So now let's take a look at a typical flat mirror, referred to as a plane mirror. And let's say we have an object, say this is a side view, right? Look inside, here's an object, maybe that's you standing in front of a mirror. All right, so we look at that. We refer to the side that you are on of a mirror, lens, anything we use throughout this optics as the real side. So wherever you are is the real side. You as the observer, specifically, not just the object, but you as the observer on the real side. The other side of the mirror or lens, in this case the mirror, we call the virtual side. So kind of makes sense to think virtual reality. It's not really there, but it seems kind of real. If you look in a mirror, it seems like that's really another room in there sometimes. All right. So let's take a look at how we can actually find the image. It's based on the light that leaves the object and reaches your eye. So we'll start off with an incident ray coming off the top of the object here. Hits the mirror. We know the law of reflection says that if we measure from the normal line here, the angle of incidence will be equal to the angle of reflection. So it should look something about like that. And so we see one light ray coming off the object, bouncing off the mirror, and we'll say that maybe you're over here somewhere and you see that particular light. In order to figure out where an image actually is, though, we need to have two light rays, and they need to actually cross each other for an image to form. So we'll draw another incident light ray down here somewhere and do the same reflection off. I'm not putting the details of the normal line in there because it's going to make this picture really crowded. But if you go through, draw this on your own paper, you really should draw out the normal lines and measure the angles to make sure things kind of show up where they're supposed to. So now we have these two light rays here, reflected, the red ones here, and they don't come together, right? They don't intersect with each other. So you're not going to get an image over here on the real side. But your brain does form an image. I mean, you look in a mirror, you see something there. And so what we can look at is the idea that if you take these two reflected rays and kind of follow them back until they do intersect with each other, they intersect back over here on the virtual side. And so your brain will actually see an image then. You'll look at that image on the back side, the virtual side of the mirror there. So now you know where the top of the object is. And so essentially then all the light coming off of the object at all points along the way that reflects off the mirror comes back to your eyes, sends that information to the brain, and produces the whole image that you see in an instant. We're just going to draw a couple because we only need two light rays to cross. All the rest of the light rays coming from the top of the object should go to the same place as well. You can try it if you'd like to. That's why it doesn't really matter where you draw the light rays to. So to simplify things, then we also look at the bottom of the object and we do the same thing. We'll take an incident light ray coming in and it reflects off, and we'll have another one because we have to have two. So we'll have another one go to another point on the mirror, reflect off according to the law of reflection. Again, these two reflected rays here and here do not cross each other. All right, and as a result, your brain then follows back and finds that point on the virtual side where it seems like the light would have come from for them to be following that particular path. Please note that these two reflected rays here do cross, but they're coming from different parts of the object here, so they're not going to be any kind of image here because they're two different things there. So there we have the top of the object, now we have the bottom of the object, and so we can simply then fill in the gaps, right? You make a pretty safe assumption that if the bottom's here and the top's there, everything else is going to be in between. Now let's look at how we specifically describe the images formed by mirrors. We'll look at the four properties, and we will describe them specifically for the flat mirror that we just looked at. So the first is location of the image. Is it in front of or behind the mirror is the first part, and then also specifically where in front of or behind. So if we go back and look at the image again, we can see that the image itself is about the same distance behind the mirror as the object was in front of the mirror. Hopefully you recognize this. If you look in a mirror at home, you realize that you see yourself about the same distance back behind the mirror. Alright, so the O is for orientation. It's which way the image is oriented. Is it pointing up or is it pointing down relative to the original object? So in this case, the object is pointing up and the image is pointing up, so we refer to that as being upright as we look at it. See, next is size, and again that's just what it is compared to the actual object. Is the image the same size, reduced, or magnified? So again, we look at the image here, it is the same size as the object. Sometimes they might look close in some of the examples we're going to do in future mirrors and lenses, and so you might have to measure them to see if one's larger or smaller than the other. Last, we have the type of image. It's either a real image or a virtual image. So in this case, since it's on the virtual side, it's a virtual image. A real image would be a case where these reflected rays, so this reflected ray here and this reflected ray here, really do cross over here, which we will see with curved mirrors and lenses, some situations where those light rays actually do cross each other and form a real image. So to wrap it up and kind of summarize, for plane mirrors specifically, the lost properties would be the object distance is equal to the image distance that appears behind the mirror. The orientation is upright. The size is the same. There is no difference between the object and the image size. And the type, it's always a virtual image. It always looks like it's on the back side of the mirror. And then one last behavior is that the image is reversed left to right, which is true for all reflections, no matter what type of mirror it is. So again, your left hand looks like your right hand in the mirror image with that. So we don't deal with that in terms of the diagrams because that is always true for the reflections. So that finishes up the flat mirror reflection based on the law of reflection.